Let us start the discussion. Well, today let us, before going to the news topics, let us recapitulate a few points again, because this is the heart of the discussion. And just 1 second. This is the heart of our discussion. You have to use those equations again and again. And so it should be clear to everybody. So I am discussing this Cauchy's theorem once again, Cauchy's equations. What we have done here, first we have to know there is a point or particle in space which is defined as equal to p. Now through this particle, we have our three mutually perpendicular axes, py, px, and pz, which is passing through p itself. And our idea is here, what we want to prove that if we know the stress components passing through the p along x, y, and z, then for this time, for any particular normal, then we will be in a position to calculate the stresses on any plane passing through that p with different normals like this. Means, say, the point P, which is at the center or origin of the three mutually perpendicular axes, that is x-axis, y-axis, and z-axis. Now, if we know the values of the stress existing over the zy, xy, and xz planes, and then any other plane which is passing through this point P but with different normals can their stresses acting over those planes can be calculated by using these particular stresses itself, particular values of stress itself. Now, let the three mutual perpendicular planes are x, y, z, and let the arbitrary plane is identified by the outward drawn normals S. What we do here, any plane which is passing through P, that can be an infinite number of different planes, and every plane which is passing through P should have a normal, and its plane is defined by its normal n. And first we are getting is certain direction cosines nx, ny, and nz, which is the cosine of the angle subtended by this normal n with x-axis, y-axis, and z-axis. This is the cosine of the angle subtended. It is just a number, maybe cos 30, maybe cos 50, or maybe cos 45, like this. And you have the value of this. This is known as the cosine, direction cosines. And if you multiply the area or any length with this direction cosine, you will get this x-axis along the y and y axis, which we'll soon witness. Thus, nx, ny, z are the direction cosines along x, y, and z itself. Let us consider a simple tetrahedron. Means, why tetrahedron? Means it's a triangular pyramid, means all its sides are made of triangles. And this triangular pyramid tetrahedron may have four triangular sides and 6 straight edges and 4 vertex corner. And one of the corner is located at P, at the center point of the three-dimensional axis. Now, three-dimensional coordinate axis, and the inclined face having its normal parallel to n. Now, there is three planes of this tetrahedron. One of these is along xy axis, another is yz axis, another is xz axis. Three planes are just kept along these three coordinate along these rectangular coordinate planes, and the fourth plane is ABC is steps is away by distance h from P to the from by distance h from the original point P itself. If the tetrahedron is isolated, let us isolate from the concerned body, and if we consider a three-dimensional free body diagram of it, you will see that the it will be in equilibrium under the action of the surface forces and body forces. Now, so what are the surface forces here? At least gravitational forces will act here. Maybe inertial force or maybe magnetic force may act. And body forces are all the surrounding forces acting over its body itself. Now, in spite of all so many forces, this particular free body diagram of this tetrahedron is supposed to be in equilibrium. There is no unbalanced force acting over it. Now, what we do here, the size of the tetrahedron is extremely small, and it is in the limit as we are going to make h tends to 0 itself. As its distance, vertical distance from the point P is equal to h, and if we say it is extremely small but not equal to unity, so that is the vertical distance h tends to 0, well, we'll expect that in terms of the average phases over average stress over the phases itself. Now let us have a t to the power n. Let us have t to the power n, tn, not exactly power, but the vector n along the vector n be the resultant stress vectors on the face AB. So we want that this force, this stress T is a resultant stress acting over stress, but a vector acting over the face ABC. Now you can resolve it into three components along Tx, Ty, and Tz. Both are the vectors of the normal n, and Tx is the component along x-axis, so Ty is the component along y-axis, and Tz is the component along z-axis itself. And these components are parallel to the three axes x, y, and z itself. On the three faces, the rectangular stress components are on the three faces, that xy faces, z faces, and zx faces. The rectangular stress components will be sigma x or sigma xx, means it is on the x plane and pointing towards the x-axis, pointed toward the positive direction of x-axis. Tau xy means it is the shear stress acting over the x plane, but its line of action is along the positive direction of y-axis. Tau zx is the it is acting on x plane, but its direction of action is along the positive direction of z-axis. Similarly, sigma y, tau yz, tau yx, zx, sigma z, tau zn, and zx. These are the stress components acting over the uh, over all these three rectangular planes, which is supposed to be known to us if we want to calculate the value of t itself. Now, if area is the value of the inclined face, then what happens? If area is the value of the inclined face, what happens here? Uh, the area, the area of BPC, the projection of the area ABC on the YZ plane. It is a cross-sectional area, which is the area of ABC multiplied by the direction cosine along x-axis itself. This is the cos of the angle subtended by the normal along x-axis itself. Similarly, area CPA is the projection area ABC on YZ plane, and projected area ABC on XY plane. Both are equal to N, A, N, Y, and A, N, Z. Now, the body face components. The body face components in X, Y, and Z will be, say, body force components is there X, Y, and Z is equal to gamma X, gamma Y, and gamma Z. This is the body force acting over this particular bar. And the logic behind it, a particular body existing in the space is always supported by its external forces which acting over it, and the support, reactions given by the external forces, by the reaction by the support itself, plus the body forces we have to brought into consideration. Body force means other than the external force, the particular resonatic bar or body has a similar existing force by itself, means which the magnetic force may act on it, say inertia force may act on it, at least gravitational force, its own weight is also acting on it. Now, we say that the body force component in xy direction is say gamma x, gamma y, and gamma z, respectively, which is per unit volume of the area itself. The volume of the tetrahedron, the volume of the tetrahedron is equal to one third A into H, where A is the area and H is the height of the prismatic tetrahedron, where or which is also the perpendicular distance from P to the inclined edge. Now, for equilibrium of the tetrahedron, sum of all forces in x direction, y direction, and z direction must be individually vanish. Otherwise, there should not be the unbalanced force. So, all the forces along x direction is equal to Tx, the component of the external force T along x-axis multiplied by the area of the area of the face ABC minus sigma x, or the stress acting normal, the normal stress acting along x-axis and on x plane, multiplied by the ANX, which is ANX is the component of this area A along x-axis, because it is being multiplied, A is being multiplied by the direction cosine NX. Tau yz, it is the shear stress acting along acting on x plane but along y x-axis and along x direction, acting on y plane along x direction, multiplied by a n y. It is the uh, it is the component of the area A multiplied a n y is the component of area A multiplied with reaction cosine n y, which is the cos of the angle subtended between the normal of A to the y-axis, minus tau zx, which is the shear stress on uh, acting on jet plane but acting along positive direction of x-axis, multiplied by a n z, which is cross-sectional area of A of the AB triangle ABC multiplied by the cosine vector, um, direction cosine of z-axis of the normal with the z-axis. Its z-axis means the cos of the angle subtended by normal with the z-axis itself, plus one third AH into gamma x. AH is the volume of the tetrahedral multiplied by the force component of body force, which is along x-axis. So this must be balanced, and it must be equal to 0, means there all these 3, 4, 5 forces are balancing each other. In the by if you cancel A, which is common to all the terms, then Tx is equal to sigma x nx, tau xy, tau ny into ny plus tau zx into nz minus one third h comma x. Similar for the similar explanation will applied, so that we can find Ty and Tz is the component of the external force x along x-axis, y-axis, and z-axis. We know the height of h of this tetrahedron is extremely small, tends to 0. So we can assume that if h tends to 0, the oblique plane will pass through the point P. It is about to pass, but not exactly through, but infinitesimally away. Then average stress component acting on the force will tend their respective values at point P, and so all the at the average stress component acting on forces will tend their respective values to point E. So this will be like look like this. Just 1 second, please. Okay. So this equation Tx as h tends to 0, this equation Tx, Ty and Tz will comes to this particular form. This equation is defined as the Cauchy stress formula. And here we have 9 variables, 9 rectangular stress components at P, sigma x, sigma y, sigma z, as well as tau yx, tau zx, etc. And actually, among these 9 forces components, only 6 are exist and independent. That is x tau xyz, xy is equal to tau yx, and tau zx is tau zy, and tau zx is equal to tau xz. This idea is known as defined as the equality of stress cross shear. The cross shears are, what is this? Tau xy is the shear stress acting on along x-axis and on x plane, but it is acting along y-axis. And this is shear stress acting on y plane, but acting along x-axis. So these two stress is supposed to be equal to each other. Same is the case of here and here. Thus, the equality of stress, the shear, with these three results above the above equation can be written as Ti, I is x, y, z, then nx, Ti, nx tau ix, ny tau ix, and nz tau iz, or n nj into tau ij, sigma j nj into tau ij. Where ij, I and j stand for x and y and z. And we know sigma is, can be written as tau xx, sigma, or say tau xx, and tau zz are like this. Now, the P, the normal stress acting on the plane ABC, can be is now is into have can be resolved, can be written like this: T square is equal to T square, Ty square, and Tj square. Now, this phase T may have one normal components and one shear component acting over the plane ABC itself. So we can write T square is equal to sigma n square and tau n square. Along this equation is also valid. So the normal stress is equal to the projection of Tn along normal. It's also equal to the sum of the projection of the components Tx, Ty, and Tz along n. So thus sigma n square is equal to nx tx multiplied by the cos vector tx is the component of the vector t along x-axis multiplied by its cosine vector along x, direction cosine along x, plus ty, the component of t along y-axis multiplied by the cos direction cosine of ny along y-axis, and Tz is this Tz is multiplied by Nz, direction cosine of the normal n along y-axis, z-axis itself. So if we substitute Tx, Ty, and Tz from the above equation, then we get sigma x is equal to nx sigma x, nx sigma j, n square z, and 2 nx ny tau xy, ny nz tau yz, nz nx tau zx, etc. And we can use this value, use equation t and t square to calculate the value of tau n. Tau sigma n can be calculated if we know this value, and if we know sigma n as well as t, then we can calculate the value of tau n itself. Okay, let us go for some other cases. Let us come back to principal stress once again. We know, just we have proved how this stress comes into along. We have seen that the normal and shear stress components can be determined on any plane with normal n using the Cauchy's formula. The normal stress and shear stress. If a resultant, if a stress exists on any plane which is uh, parallel to the with line of action is parallel to this normal, then by Cauchy's equation we can have its component along x, y, and z axis like this: nx dx, nx sigma x, ny tau x yx, and z tau zx means normal stress, shear stress, and shear stress. Same, its component along y axis is n nx tau xy, ny sigma y, and nz tau y. And same is the case with this component along z axis. So we have these components along x, y, and z axis, and we know that uh, this particular force T can be solved into two mutually perpendicular direction. That is, one is normal or along this sigma n, along this normal n, or another is tau normal to the normal n itself. Now we have to complicate, we have to answer few questions here. Now we have to answer to, is there any plane passing through the given point? Say this given point P, just we have discussed. Is there any plane passing through the given point on which the resultant stress are wholly normal? In other words, resultant stress vector is along the normal. Means we have to find out the extra whether that external force acting, external force T acting over the point P and over that prismatic is the triangular pyramid. Is this resultant stress are wholly, is there any point or any position where the resultant stress are wholly normal? What is the plane on which all the normal stresses is maximum and what is its maximum? So what is the plane? Two questions, and what is the plane in which tangential or shear force is maximum and what is its magnitude? We know our principal stresses. In principal stress is the what is the maximum, what is the minimum stress exists over a particular plane or a particular point here, our line of discussion. And we know when the press is normal stress is the maximum, there is no shear stress, and when normal stress is minimum, there is no tangential stress. And there exists a point in between the maximum and minimum where the third normal stress exists, which is also there. There is no shear stress. And but there exists also on plane where the tangential or shear stress is also maximum. But for those case, this normal stress may not be equal to 0. So what we have to know, what is the plane? What is the plane? And thirdly, what is the plane? We have to find the orientation of the plane where the resultant stress is totally normal. There is no shear component if you resolve along the plane. And well, what is the angle? What is the plane? What is the orientation of the plane where the normal stress is maximum? And if maximum, what is the value? And if normal stress is minimum, and what is the value? Next, at which plane where the tangential shear force is maximum and what can be its magnitude? These three questions we have to answer. What is the plane where principal stress is maximum minimum? What is the plane where shear stress is maximum minimum? How will you do? Let us assume that we have such plane whose plane n with direction cosine nx, ny, nz. We have such plane where whose the normal subtend by an angle. There is a normal whose subtended cosine of whose subtended angle along x-axis is nx, cosine of whose subtended along y-axis is ny, and cosine of whose suspended along z-axis is nz. so that the direction cosines. This is given and known to us. Means we know the orientation of the plane along x of the normal along x, y, and x axis. Or in turn, we know the orientation of the plane in the x, y, and z axis, z coordinate axis. Now, let sigma on which the stress is wholly normal itself. So here with on this plane there is no shear stress. If we try to resolve this force, resolve this external force along the plane and normal to the plane, we'll find it is totally normal to the plane, and that is thus there doesn't exist any shear stress itself. Now, so sigma be the magnitude of this stress vector, which is totally normal on this plane, and thus we have t to the power 2t is equal to sigma n. Sigma is not sigma multiplied n, but sigma prefix n. So thus the component of this along x-axis, x, y, and z-axis will be the value of sigma n, value of sigma sigma multiplied by the direction cosine x multiplied by direction cosine y, and multiplied by direction cosine z itself. Now, from the Cauchy's formula, we subtract above equation. Say what we will have then, sigma x minus sigma equal to nx tau xy ny plus tau xy z equal to 0, tau xy nx sigma y minus sigma ny plus tau yz into nz equal to 0, and tau xz nx plus tau yz ny plus tau z sigma ny equal to 0. Thus, we have above set of equation as the three simultaneous equations. Now, as at present we don't know the cosine vector, cosine vector in x and y and z, the three direction cosine vectors, direction cosine. So the direction cosine will define the plane on which the resultant stress is acting normally. But we have to know this thing. If we know, then we can have the position or direction of the plane n, and the plane on which this plane is normal, over which the resultant stress is totally normal. Or we can say that on this plane, the normal stress acting is the maximum or minimum, or on this plane, the principal stress is acting. So we have to find this particular direction cosines first. So first of all, the easy and trivial solution is all this x and y and z should be 0, so that this equation will satisfy. But it will not serve our purpose because we know nx and y and z is not totally 0. So we have to find a more difficult way of calculating it. If we put down the matrix of these vectors like this, then and make the addition and subtraction, the above equation will take this particular form, where we have a cube root of sigma, a square root of sigma, and a sigma square, and a single sigma, and there is no sigma at all. And these components can be this component this component of sigma cube, sigma square, sigma, and no sigma can be less like this. The three roots of this cubic equation can be designated as sigma 1, sigma 2, sigma 3. These three roots are real, and you have to solve this cubic relation. And there is three equations and three unknowns, and we have one cubic equation. So we can substitute any of these three equations in equation 2, and we also may solve corresponding nx, ny, nz to avoid trivial restriction. Then we can have this condition: nx square ny plus ny square plus nz square is equal to 1, means square of the reaction cosine of the normal is equal to 1 itself. It's addition of the square of all the normals, all the reaction cosines of the normals is equal to 1. If we use these four equations, then we'll have, um, with this sigma, this there will be a plane, and this plane on each of which the stress vector is wholly normal and called principal plane. Just I have told discussed that we'll have the plane where the stress vectors are totally normal, and which is the principal plane, and corresponding stresses are principal stresses, because we know when when at the maximum normal stresses, which is the principal stresses, there is no shear, and since the resultant stress is along the normal also, there is no tangential stress on the principal plane. So the principle is known as shearless plane. Now, the stress we have came to a condition, stress invariance, where from the last equation we put L1 is equal to sigma x plus sigma y plus z, L2 sigma x sigma y plus sigma y sigma z plus mz sigma z sigma x minus tau s y square, tau yz square minus tau zx square. And this equation can be put in the matrix form like this, where sigma x and sigma y are diagonal and tau xy is like this. This is also diagonal. That is, which is existing here like this. And tau y, tau z square, tau xy is here. Same is the case of tau uh, and tau y and tau z, and tau yz and sigma y sigma z and tau yz and tau xz and sigma x and sigma z, tau xz and tau xy. So this equation can be written as sigma square minus L1 into sigma square, sigma cube. This is not square but cube, minus L1 sigma square plus L2 sigma minus L3 is equal to 0. The quantities L1, L2, 3 are to be known at the first, second, and third variables. Means this is first, this is second, and this is third variables. Because here we can make the matrix accordingly. That is, yes, x sigma y, sigma z, all three are diagonal here, and the two tau xy, then tau xy and tau zx here, and accordingly we have to put all the planes to get this particular matrix itself. These L1 are the first, second, and third variables of the stress maximum. At a vibrant is one whose value does not change when the frame of reference is changed, which means our frame of reference is our rectangular coordinate axis x, y, and z. But as per our this present theory, if we use another rectangular coordinate like say x dash, y dash, and z dash, then thus at the same, but it should be supposed to be at the same point. Then, with respect to this frame of reference, the rectangular stress components are sigma x, sigma x dash, sigma y dash, sigma z dash, and then the values of L1, L2, L3 are shown in equation 536. Will show that sigma x and sigma y plus sigma z is equal to sigma x dash plus sigma y dash and sigma x y z. Thus, L1 is L1 dash, L2 is L2 dash, L3 is L3 dash. So, if we find the value of L1, then L2 and L3, then this L1, L2, L3 can be used to know the value of sigma over any other plane of reference other than its original plane x, y, z. It can be x dash, y dash plane, here L1, L2, L3 are all same, so that you can find kind of value of sigma on that different axis itself. Principal stress, at any point it depends only on the state of stress at that point and not on the frame of reference. Because describing the rectangular stress components here, but if the reference is changing or the rectangular axes are changing, will hold the principal stress will not change itself. If x, y are two orthogonal frame of reference, then the following cubic equation, sigma square minus L1 sigma square plus L2 sigma minus L3 is equal to 0, etc. And this same equation with L dash, L2, L1 dash, L2 dash, L3 dash must give the same solution for sigma. Since the two systems are arbitrary, two systems are actually arbitrary, the coefficient of sigma square, sigma, and the constant terms must be equal. That is same proof we are doing. L1 must be equal to L1 dash, L2 must be equal to L2 dash, and so. The principal stress, the invariants are L1 in terms of the principal stresses. There are three invariants are L1, sigma 1, sigma 2, sigma 3, and the same is sigma 1, 1, sigma 2, sigma 3, sigma 3, and sigma 1, sigma 2, sigma 3 in terms of the principal stress itself. The principal planes, thus we have found it, is corresponding to a given state of stress at a point and can be shown to be mutually orthogonal. To prove this, we make the use of Cauchy's theorem, we just corrected like this. Let n and n dash be two principal planes and sigma 1 and sigma 2 the corresponding principal stress. Then the equation projection of sigma 1 in the direction n dash is equal to the position of sigma 2 in the direction of n. That is sigma 1 n dash n is sigma 2 n n dash. If nx, ny, z the direction cosines of n and same n x dash and y dash in direction for n dash, then the corresponding to the above equation will be, and from this above equation, nx dash, ny, n1 dash sigma 1 multiplied by this sigma 1, sigma 2 multiplied by this itself. This thing is equal to each other. Okay, we are at the finishing end of our class. Thanks for your patient hearing. I will go further the next tomorrow by going to the next problems itself. Thank you.